what I was trying to really refer that. Okay, so we have 1s 0 and 1s 1, right? Those are the inputs, right? And now in the output side we have a Z0, Z1, Z2. Again, as I said, right? Don't confuse with the little Indian and big Indian notation, right? So we can have a 0 0, 0 1, 1 0 and 1 1. Once you add, what will be the values, right? 0 0 1, 0 0 1 0, 0 1 1 1 and 1 0 0. So now what I should do, if I wanted to get an expression for Z2, I mean, right, I will make a Karnaugh map, right? Yes or no? Right? And then get an expression for Z2, Z1 and Z0. Yes or no? So we should be able to get an expression, right? I mean, we can do it, but but the interest of time, I'm not doing it. Yeah. So once you get these expressions, right, we just need to really draw the diagram, right? Okay, as we said, so we'll have a 3 latches, and again this CK is a enable input. It's connected to 5, so it's in the next page. Okay, what is the Z0? So Z0 nothing but it's a 1 0 and 1s 1. So where do I get 1 0 and 1s 1? Those are the input, right? Okay, so we have this 1 0 and 1s 1, and of course it's a simple AND gate, right? We have an AND gate, and similarly Z1 I derive the logic and connect here, and for the Z2 also it's just 1s 1 bar. I'll just connect it. I think I have in the next slide here. Yeah. And now we see, right, all the enables are connected to the 5. Right? Again you see, right, at a moment it looks like a bit complicated, but once you know the K maps and all, it's easy to get. Good. So there are a few other things. Okay. Now look at this code. There is some issue with this code. I mean, it's fine, it works, right? But there is some issue with this code, and again it's concerned with the students and grades, right? So what is the issue? Okay, no else statement, right? That means we'll get a latch. Okay, so but the problem is that if the marks are, let's say, okay, one student got 2 marks, what should be the grade, right? So now the next student got, let's say 10 marks, or let's say 9 marks, sorry, pass, right? Okay, so now next student got 2 marks. What is the answer? Fail, right? And the next student got this time 11. See how come, if the 11 student 11 marks means fail? I mean the circuit is, I mean, logically fine, it's same, right? But again you see, right, when you, let's say, if you are asked to do such thing, right, when now it says that, because if you say 11, I mean it all depends upon what was the previous state. If the previous state was, let's say, the 7, I mean then it could have been, let's say, pass, and the 11 also will say pass, maybe instead of excellent or something like that, right? So basically, right, so here definitely, right, we should have an else statement, right, and then model the circuit. Of course here synthesis everything we can do, but it's not about that, right? So here you can also think about logically what should be the right way to model, right? So now if you do model something like this, so we'll have issues. That's what I want to highlight. Okay, good. What? Which one? Internal register? Okay, okay. So of course, I mean, we can really combine this, right? So now we just simply set output, right? Okay, but as I said, the left hand side of the variable should be reg, right? Right. See, in always statement, the left hand side of the variable should be always a reg, right? So that's the reason we declared this one. Otherwise, we can also simply write output and reg. That's fine, and then you combine this. Okay, good, fine. Okay. Okay. Now I think I'll skip this case statement. Again, in the case statement, right, it's a nested if else, right? If else, if else, if else if will check, and again in any one of the branch if you miss, it's going to be a latch, and if you have a complete list, it will be combination logic. Okay, I'll just skip. Okay. Okay. So now I think this is what it's mean. I mean this is okay. There's a simple example are there. Okay. So again think about, let's say, this circuit and try to draw the kind of a circuit which you get it. It's very simple, I guess. So try yourself. Whenever the clock A changes or current state changes, you enter into it, and if clock A, the current state, right? Again, it's a latch. What should be the enable signal? Clock A, and of course, right, next state 0 is connected to the current state 0. I mean 2 to 1 to 1 and 3 to 3. So this will be something like this. Yeah. Okay. Good. So now this is an interesting part. We'll spend definitely some time here. Okay. There are 3 bits, right? I mean 0 to 3, total 4 bits. 0 is connected to 0, 1 is connected to 1, 2 is connected to. Yeah. Yes, but now, I mean, of course, right? So now at that, so now if you see, right? Okay, yeah, I understood your question. So for instance, current state change. So we should enter, right? Okay, now then you are anyway you are checking clock A, right? Yeah, and if clock A change, right? If the clock A change, we should also enter the block, right? Again, think about the latch functionality, right? Right? If the input change, if the enable is active, we should send the out, right? If enable got changed, right? If enable got changed, again we should go into the loop and we should change the output. But again, you see, right? Then I think there's one thing which I forgot to tell you, right? In always block, when you are writing, the kind of the modeling the combination logic and all, right? We should list out all the signals which are on the right hand side, right? So yeah, so then it will correctly capture the behavior. If any of the input changes, it will just trigger. Now if you see, right, no, again you see, right, I mean, as I said, right, in the hardware I have only wire, I have a latch and I have a flip flop. Now what you are saying that you will not put this one, right? But again you see, right, in your simulation what will happen, you will get something, but hardware, somehow it gets the same thing. Hardware just generate the warning and most probably will get the same circuit, but the problem is that you will have one behavior in simulation and one behavior in synthesis. Okay, good. Okay. Now, I mean, we have latches, right? Latch can also have kind of a reset pin, the preset pin, right? And we can also have enable. Now in this, let's say kind of this let's say part of the circuit, what we have is kind of we have something called reset or set or and a clock X or current state. There are like multiple things. Now if you look at the code, right, what we are saying, if not reset, so we should say that the next state equal to 12, else if next state equal to, let's say 5, and again else if clock X next state equal to current state and else is not mentioned. So now first of all, because it looks like maybe a flip flop or something, right? But again, as I said, there is nothing like a passage or anything. It cannot be a flop. It could be a latch because one else block is missing. Now again, if you see, right, so we have, let's say we have a priority, right? Again, if you look at the code, right, first we are checking if block and then else block and then again we have else block, right? So now we have some kind of a priority, and now you enter into this loop whenever anything changes, right? So that means reset is also kind of a asynchronous, and I mean set also is an asynchronous. If any of those changes, your output should really change, right? Is it clear? Fine. Okay. Now how do we really get the logic correctly? So now what we are thinking about, we were thinking about a D flip flop, D latch. We have a D input Q and we have enable, and now we are thinking about, we have a kind of a preset pin and we have kind of a reset pin. Again the preset could be active high, it could be active low, the reset could be active high, active low. Again you see, right, whatever the circuit comes out, it depends upon what kind of cells I have, right. Is that clear so far? Okay, now how do we really go about designing this circuit? I know that next state is what? 4-bit signal, right. I only know that definitely there will be 4 latches, right. There will be 4 latches. Okay. Now how do I get, let us say, first latch? So how do I get my first latch? Okay. Okay, now let us say, okay, I am working on the next state 0 or whatever. Okay, let us say this is next state 0, I will just kind of abbreviate with the next state 0, I am working for this one. Okay, I know that, right. So this is a D and there is a Q, right, and then there is a enable pin, right. And now, so since it's a, there is a asynchronous pins are there, right, asynchronous signals are there. So now I should also have maybe a kind of a flip flop with maybe asynchronous pins. Okay. So now if I look at, right, so in the, I mean the solution, so I have, let us say, I mean first of all, okay, next state 0, right, let us try to stick with this one. So we have a CDN, right. So CD stands for the clear data, clear pin, and N stands for it's a active low. So now what he is trying to really say that, so we have this CDN pin which is active low, that is what is synthesized. So let us try to stick to that, exactly the same thing. Yeah. Okay. Now as I said, synthesis means what? We have to derive the logic for the D input, we have to derive the logic for enable input, and we have to of course connect, let us say, Q, right. So proper signal. So how do we really get? Any ideas how do we really solve it? Okay. Again, as I said, right, so we just need to know about truth table, nothing else. Okay. Now if I say that I have a reset, right, and I have a set and I have clock X, right. Okay. I am now simplifying for maybe the next state 0, right. So this is my output, these are my inputs. Okay. Now, so what we said, it's a 12, right. So 12 means what? 1 1 0, right. So 5 means 0 1 0 1. So now I am talking about this first bits, right, 0 and 1. Okay. Now if you look at the code, right, it's a not reset. Not reset means reset should be 0, right. If it's 0, what will happen? I mean irrespective of this one, na, what is my output? 0, na, right. And now reset is 1 only, then I will go to the next signals, because if is a higher priority, right, if reset, right, if as long as 0, then I do not even look at the other signals. Yeah. So now if I want to go to the next one, reset should be 1. After reset, if the set equal to 0, right, if the set equal to 0, I do not even look at the clock X, I do not even look, right, it does not matter, right, like the dash means now it could be 0 1, does not matter, right. But here in this case the reset should be 1 and the set should be 0, and again the clock X could be 0 1, does not matter. So what will be the output? It is a 1, no? Yes. Okay. Now if the reset equal to 1, set equal to 1, and then if the clock X equal to 0, what will happen? What will happen? The next state is equal to current state 0. Yes or no? Yes or no? Okay. Now, yeah, understood, right? Okay. Now look at the circuit. So here this output is 0, right? What actually this CDN pin will do? If you give a proper active signal to that, it will set the output to, it will set the output to 0. Yes or no? Okay. Now in the solution, he is using only the flip flop with the CDN pin. That means his library only has the latch with the active low clear pin. So then what we need to do is that we need to really redirect the input, let's say truth table, appropriately to the appropriate pins, right. So now let's say if I ask you this question, if I give this CDN, let's say, right, that input 0, what will happen? If I give the CDN input 0, what will happen? I mean, according to the truth table, what will happen? Output 0, no? Yes or no? Because it's a CD pin, it's an active low pin. That means if you give 0, then only it's active, and then output should be set to 0. Now, according to the truth table, now what signal I should connect it to? Right? If I simply connect what? Reset, right? Yes. So now the CDN, simply if I connect the reset, what will happen? Just, I mean, let's connect it and check it, right? There is no harm, right? Reset equal to 0, what will happen? 1, right? Reset equal to 0, what will happen? Output is set to 0. I mean, it's satisfying the truth table, right? Okay, good, right? So since we have only CDN pin, that means in the output, so this, let's say, right, output is set to 0, and now we connected this one, and that means, okay, we have completed this entry, right? Yes. Now what is left with? We left with these 2 entries, okay? We left with these 2 entries. In these 2 entries, what we should do? We have to make the latch open. First of all, if you wanted to send the output, right, to the queue, what we should do? We should make the latch open. So latch open means we have to derive first. We have to derive first enable condition, right? So what is the enable condition? Now looking, I mean, you know, look at the truth table and tell me what is the enable condition. So in enable condition means in these 2 cases I should make the flap, let's say the latch open. You tell me what is there, what do you see there? Some kind of expression can you come up with? I mean, of course we can really draw the truth table and derive it, but I just wanted to save some time. This enable condition, right? Reset should be what, like 0 or 1, right? So can I say it's a compulsory reset, right? Now its reset should be 1 and set should be 0, right? I mean, of course, right? Now I wanted to say that set should be 0 means not set, no? Because I wanted to make it 1, right? Enable pin is what, active low or active high? Active high. So that means I should supply 1, right? Right? So I should take not set. Okay. Then other condition, again reset should be 1, this one, and right, and other condition, I mean, I can neglect, right? So not clock X, right? So right, reset should be definitely 1, right? And of course I can leave this, but this should be 0, right? So that means not clock X, right? So now what I can do is that just connect this logic to the enable pin, right? That means in these 2 conditions you are opening the latch. Okay, now what is the D input? What is the D input? Now you should send 1 once, right? So of course current state we can send directly, right? But we should also send, so we should also send 1, right? So when you send 1, what is the D logic, right? So definitely CS0, right? Okay, and we should send 1 when, right? If set, but when is the condition? Reset should be 1, set bar, okay, and then that time you are sending 1, it's a 1. Yes, okay, now yeah, got it, right? So basically, again, as I said, right, the problem looks a bit complicated, right? But when you start really doing it, right, it's simple. Again, you just need to ask yourself, what is the when should I really open the latch? Okay, now for instance, it could happen that there was a kind of a latch with a preset pin which is active high, right? We'll just take this condition, right? Yes or no? Right? So now since we wanted to match the solution which is given, we're just taking this one. Now in this case, for instance, we have active low clear, right? So what is the guarantee that we have a latch with CDN? So now I have a latch with only CD signal, it's active high. What should I do now? Just negate the logic, right? See, instead of connecting the reset, you connect not reset. Yeah, is that clear? Okay. So do you want to try for the next, let's say, bit CS1 on your own? So maybe I'll just zoom in this part of the circuit. And again, as I said, right, I wanted to match the solution which is given in the book so that I can cross check. So now for the current, let's say this the next state one. So if you look at the solution, he used a kind of a latch with a CD pin, right? It's not a CDN pin, just wanted to know really, just right. So now if it is CD pin, of course, now again if you look at, right, it's a 12, right, 110 and 0101, right? So in both cases it's connected to, I mean it's a reset or not reset or a set, it's a both 00, right? So that's what we have. So now what he's trying to really do is that, okay, this both cases I'll really map it to the CD pin, but now the CD pin is active high pin, right? It's not a active low pin. So now in these two cases, if I take this condition like, okay, now if you look at, right, so we have reset bar plus set bar, right? So what is the condition? Reset bar or plus set bar. So what will happen? Either one of them is 0, right? For instance, so one of them is 0, reset bar will become 1 or the set bar will become 1, right? And then I can connect it to directly the CD, right? So now assume that instead of the CD, we have a CD pin, CDN pin. If it is active low, what we should do? We should simply take reset and set, right? If any one of them is 0, the output is 0, right? And one case only will go to the next one, right? So 1 case means this is a 1 actually, right? So in this way, right, so we can really, solve all these questions. Okay. So just again, I just wanted to really emphasize that, okay, whatever the synthesis tool is trying to really do is not really magic, right? With a pen and paper, what we are trying to really do, it's doing the same thing, but maybe it's automated, right? And of course, as I said, right, maybe with a pen and paper, we are a bit limited, but again, so tools, algorithms and all, we can do much better. But this is a principle. It's also try to derive this kind of expressions, try to simplify, come up with the equation. Okay, and now onwards you should really not only think about writing the code, and if you write the code, what will come out, that you should think. Okay, good. So if somebody needed, so I just kind of pass on all these things. So okay, good. So let's move on. Okay, again maybe here let's wanted to emphasize again. So CD, CDN, okay. So you see, right, one of the let's say latch, he used only the PD pin, right? So 1100, right? So 0101. So now in this case, right, we have 11. For that one, he is used only the PD pin. So that you will find it in the solution. But again, the same procedure we have to do. Okay, good. Now look at this code. I think. The code, I think I misplaced. Okay. So, okay, the code is missing, but anyway, it's fine. Okay. So let's come to the flip flops. Okay. So as I said, this is what the slide summarizes. Let's not read the slide, but let's try to kind of make a statement. So whenever you have an always statement, and we have to look for an event. What is that event? It's a positive edge of the clock or the negative edge of the clock. So when we have this kind of a edge event, then only you will get a flip flop. Okay, that's our standard rule. Yeah, so this we call it as a clocked always statement or something. Okay, now, so try to kind of draw the logic for here in your own terms, right? So that this kind of the diagram which I have drawn, it looks really different. So try to think about this code and try to draw your own diagram. You can think of, right? So there is a flip flop with only D input, clock input, hmm, hmm, and a Q output. Yeah. So basically we can think of, right? I mean, we'll see what is exactly this means, but okay, we can think of that. Okay, we have a D flip flop, right? So D. Okay, I mean, so let's assume that okay, we have a only positive trigger, right? I mean, right? So then we should really connect with the negate, yeah. But if you have a negate triggered flip flop, you can simply connect the clock. Yes. So CL was CK, right? And now the D input, right? Right. Of course, if you see, right, if there is a control signal, right, it's like a multiplexer with a control. I'll use the control. If it is a 1, it's a A, it's a B, and then this will go here, and then this Q is connected to Z. Okay, now, and what is this is that the library which he is using, right, it has some inbuilt mux, that's all. And now the mux, one input should be connected to the D1, 0th input connected to be 0, and then your select signal should be connected to the SD. So now you can think of this mux is really residing in the flip flop. He has that one, doesn't matter, yeah. Okay, it's the same thing. Okay, good. Now again, right, so here I mean I just want to again know, so here again since we have a passage of clock, so this will definitely counter will be a flip flop, but again the counter you are adding, right, but you are not adding a generalized value, it's a plus 1, right. Again the same holds true that since you are adding 1, we can really optimize this logic and connect it to the counter. So let's not do it, yeah, there are few other things. Okay, good. Now, okay, can we spend some time on this? Again think about how you are really going to, let's say, design it. Okay, this is a up down counter, this is an up down counter, yeah. So whenever the control signal equal to 1, you are doing up counter, and whenever the signal equal to 0, you are doing up, let's say, down counter. So now how do I really kind of come up with a circuit for this one? So try for 5 minutes or so. Again, the counter is not a big counter, right? It's just only 2-bit counter, 0 0 0 1 1 0 1 1, and whether it's a TL or whether it's a TL Verilog, whether it's a anything, ultimately you have to end up in a Verilog. Of course, the code you are not writing, right? The TL Verilog also translate to your Verilog, right? Or chisel also it's a Verilog, right? And again you see, right? So having the knowledge of how the tools works, the knowledge of how synthesis will happen might really help you to debug your designs. Again you see, think about, right, so control is 1-bit input, counter could be 2-bit input, right, correct, right? So now 0 0 0 1 1 0 1 1, right? If the control equal to 0, you down count from current state to the next state, and if the control input equal to 1, you will up count. So then you can come up with a truth table and derive the equations, right? Yeah, yeah, I know. I just wanted to really bring out the complete idea. Okay, if you see, right, the simple method could be this, what I just again I say, right. So control is a 1 bit input, it could be 0, and then we have to change the current state output, right. It could be 0 0, it could be 0 1, it could be 1 0 and 1 1. So when it's 0, right, what is it? It's a down counter, right. 0 0 means what is the next state will be 1 1, right, and 0 1 is a current state, it's a down counter means 0 0, right. So if it is a 1 0, it is 0 1, if it is a 1 1, it is 0 1 0, and then so control could be 1, and again the current state I just enumerate and then I will derive it. So now I will get, let us say, the next state 1 equation, next state 0 equation, right, and now I will just simply write the flip flops, right. Okay, maybe this is my next state 0, the left side one is the next state 1. So if you look at maybe the next state 0 equation, it simply says 0, right. The current 0 means from the negative input I am just taking, connecting it, right. So maybe the next state 1 equation, right, it's a bit complicated. It's now if you look at maybe this part of the equation, right, right, it's with a control bar, and this part of the equation, the last two terms, it's with a control, right. So I am just simply using again a multiplexer, right, and then just generating the first term and the second term and just connecting it, right. Okay, now if you look at, let us say, the book, right, the actual solution, he is using the kind of the flip flop with a D1 D0 and all, but again so we could also really do that. Okay, so here just what I did was, right, to just match the solution which is given, right. So he is using the flip flop with D1 D0 pins. Okay, now when the control equal to 0, right, so I will not change any D1 pins, right, I will only change the D0 pins, yeah, and when the control equal to 1, right, so I should change the D1 pins, right, because that D1 pin corresponds to the control equal to 1, the D0 pins corresponds to the control equal to 0, that is what I did, and then I derived the logic for the D1 pin and the D0 pin of the both flip flops. So since as I said, right, so the library has a kind of a flip flop where the mux is inbuilt, and again that's what the tool also does. Yeah, good. Again it just right, so take this as a kind of input and then so just work it on later. Okay, I think this should be simple. So we will have a kind of a simple next state with a current state, yeah, with the kind of a passage of the clock. Okay, good. Now, okay, just look at the example. So now we can also have multiple clocks, right. Again, take a minute or two and then come up with a diagram for this, synthesize diagram for this. Yeah. And remember that one variable cannot be assigned in multiple, let us say, passage statements, right, and under the different clock. So if you look at here, right, so this add state is being assigned under this clock. Suppose this add state also will get assigned in another, let us say, always block with a different clock. Now you have a confusion, right, what should the clock should be connected to, that flip flop, right, what clock it should be get connected to, either the first one or the second one, that means it's wrong, right. If you have a confusion, the tool also will have a confusion, so it should not be the right thing. Okay, that means any variable which is on the left hand side in a passage of the clock or negation of the clock, I mean it should only appear only once in the left hand side, it cannot appear on the right hand, let us say, left hand side multiple times. And then we have a problem, right, to which clock we should connect, that is the question. But I mean we can read under another clock, that is what is happening here, right. So here add state is being assigned in under one clock, but it is being read in a different clock, that is okay, right. So basically here you can expect that this add state, sub state are the flip flops with this VT5 clock, and maybe this DSL add and a DSL sub are kind of a flip flop which are clocked by this DSL clock, right? But of course, right, that the DSL add will take the input from this add state. So try to draw the diagram on your own. So we should be kind of in time. We'll have an example for that. We have, I think. I'll show you. Yeah, I'll just show you the logic as I said, right? So that add state and substate are the kind of designs which are clocked by this VDFI clock, and then this is clocked by this DSL clock. Of course, right? This add state you are reading, right? So this DSL add. Okay, good. So now I think this is what I think Rahul was referring to. We can have, of course, right? Generally, the practice is that we will not use the positive and negative in both, but for the sake of having, right, so we can just test, right? So here, how should be the diagram? I mean, there are, let's say, two, let's say, flops, and one flop is clocked by the positive of the clock, right? This CK. So this D or C, right? And it goes as input DQ, and this is your E. So CK is connected to CLK, right? So now the next one, the negative of clock, right? Yes, it's a AND. The DQ, and this is your D. Okay, and now of course D comes from where? So now you are reading this D and C, right? So the D should be connected to this D and this D are same. Yeah? Yes or no? Of course, both D should be the same, right? Okay. So this your, okay. So that's what we have here. So right, this D is a same D. Okay, just a different way of drawing, but it's exactly the same. Okay. I mean, both clocks was same, it's fine, but right. No, but again, you see, right? You're just I mean, this adds. So the problem is only with this one, right? So here, what is happening? It will be the same clock. You're just loading the previous value. That's all, right?
The current one will not be loaded.
Yes, the previous one. No, here also why the current one will load, right? It's if the clock was also same, it's difference, right? The clock was also same. What will happen? If the clocks are same, what will happen? So these two will also be clocked by this VT5 clock. But these are the same thing, right? You are also reading the add state value. Add state or the substate, it's again a flip flops values which are clocked by VT5 clock. Yeah, but again you see, right? So you are reading first, right? It's not like you use the current value, right? Yeah, of course. Yeah, that's what I'm saying. Only the clock will change. That's all. Nothing will change. It will give the same circuit. Only the clock will change. That's all. Right. So instead of this DSL clock, so the same VT5 clock will be there. Yeah.
Still the value is not assigned to add state, then what? So it will either take the one which is actually being evolved.
No, but you see, right? These are two executing in parallel, right? So now, right? So now you're trying to calculate a new value for it. Okay, you explain, right? But I'm just reading the previous value of the add state, right? That's what the this one here, right? The previous value you're reading. That's all. Huh? Good. Fine. Okay. Now, okay. So here I think I was trying to explain in this slide the same thing which I mentioned before. So whenever you have such a kind of the passage A, B, C, right. So in this if you see, right, you do not know which is the clock because we are using the names called A, B, C, right. So now the emphasis is that, okay, right. So we have to look at this statement and then what is the else block, what is left out. So in this case now we use A, right, B used, and of course C we used, and we did not use the CLOCK. So that should be your clock. Okay. Now again the same example, right. So what is the difference between the previous example and this example with the latches? I mean the example exactly looks the same, right, but only that, so now we have a negate of clock here, right. Earlier of course we have a passage reset or something and all, but so we have a passage of the negate of clock here. So again, so here is it like let's assume that we have a flip flop. So we can have a flip flop. Earlier what we said was, okay, maybe I can repeat, when we are synthesizing with the latches, right, we said we can have a latch with your preset and clear pins. So we can really redirect the logic, right, but we have only the CDN pin, right. So then we have to really appropriately redirect the logic to the D input, and in both cases we have to make the latch open. Yes or no? So here let's assume that we have a kind of a flip flop with both or any one of them, but we have kind of a latches, sorry, the flip flops with this preset and clear pins. So again what we need to do is that we need to really redirect this logic appropriately. Yes sir. Okay. So just let's just kind of try to really solve it again. I'll just I think I should have a solution. I just look for that. Yeah. Okay. So this is what we have. Okay. So for the next state 0, right. So we have, of course we are looking at this 0 and this one, right. Okay. So again we have a not reset, so that means 0 should be there, and set we don't care, right. Okay. And of course, right, now in this case we don't have a clock X because that is going to the clock itself, right. Okay. Now set could be anything, right, and then when you have a, let's say, reset equal to 1, so then only we look at the set value, right. So set should be 0, okay, and then we have a 1, this is a 1 correspond to this one, and then reset equal to 1 and set equal to 1, and that is a clock condition, right. So then, so we will have current state equal to next state. So again what we need to do is that again in the, I think so we wanted to match the solution which is present in the book. Okay. So here I mean in general we can have a D flip flop with a preset pin, clear pin, and again the preset could be, let's say, active low, even the reset could be active low, but again as I said, if you look at the solution here used a flip flop with preset pin active high and the clear pin active high. So now here, so we have this 0 condition, right, and we have this 1 condition, right. So the preset or let's say the reset or a clear, right. So we should take this condition. Yeah. So what is that condition? So what is that condition? It should be a reset bar, right. Now if you if you connect the reset bar, what will happen? If the reset equal to 0, reset bar will be 1, and if you connect 1 to this CD pin, what will happen? Your output should be set to 0. Is that right? So similarly, now let's talk about the preset pin, right. This logic should go to the preset pin, right. So if you apply to that pin 1, so output should be set to 1, right. Okay. Now how do we get this logic? PD, right. So what is the condition we have? We have a set bar 0, right. It's a set bar and reset. So we have a set bar and reset, we are just connecting it. Again just look, right, if the reset equal to 1 and set bar, right, so set equal to 0, right, what will happen? So set bar 0 means bar set will be 1 and reset multiplied by set will be 1, and you are connecting it to the PD, right. So if you connect the PD equal to 1, what will happen? If the PD pin equal to 1, your output bit is set to 1, right? And then these two conditions you already covered, right? So what is left out with the clock condition, right? So right, so that one you, of course, clock is connected to the clock here, and so what is the input? It's a simple current state 0. Okay, so this way, right? So we can really derive for the next state as well. Okay, so again, just to give you a kind of thought process. So maybe you do it for the current state 1. At least just to give you a kind of a time. So do it for the current state 1. Okay. Good. So for the current state 1 flip flop, you just try to really derive the logic. One case, both the kind of a not reset or a set, right, is 0 0, right? So right, so we want decide to use only the CD pin. Okay, I mean again the CD pin could be active low or active high. So as thinking the CD pin is active high. So now that means these are the two conditions. Now you see, right, what are the conditions we can simply right, it's a not reset or not reset, right? So again if you see, right, it's also to kind of, if you are a bit confused in deriving the logic, so what we can also do is that we can also simplify for the CD with respect to with using K maps, right? For all the possible conditions you list it and then get the logic. Okay, and if it is a active low, what should do is that we should get a 0, right? So take this logic, whatever you come for the CD logic, just negate it, right? I mean this way, right? So any complicated logic can be done. Yeah, good. So let's move on. Okay, maybe when you get time, so do it for 2 and 3. Okay, okay. Now just okay, 1 second. Okay. So what is the difference between the previous circuit you have seen, this circuit? Huh? It's a synchronous reset and synchronous set. Okay, good. So now the idea here is that okay, now when you say it's a synchronous preset and synchronous clear, right? Okay, so now here, I mean I could have a flip flop with a synchronous reset and a synchronous preset pins, but let's assume that I don't have a flip flop. That's what the solution says, right? I do not have a flip flop with synchronous reset and synchronous, let's say set. Yeah, now what should I do? I am left only with the whole logic. I should really redirect it to D input. Yes or no? Okay, so how do we really do that? So here, okay, so that's what we have. Okay, now try to look at what we are trying to really do. Okay, so anyway the clock B is there, right? Okay, so what we are trying to do is that, of course, if you look at maybe 12, right, 12 is 110 and 5 is 0101, right? I am talking about the next state 0, the first, let's say the flip flop. I am just trying to really put exactly the I mean kind of a bit high level view that okay, of course I have to really synthesize a D flip flop for the next state 0, right? I am there, I know which clock I should connect it to, the clock B. Okay, now the question is, I mean of course everything is a reset, right? I mean everything is a synchronous, right? So I have only a D pin which is synchronous with respect to clock. That means I should really redirect everything to the D input itself. Okay, but again, right, so I have a kind of a priority here. Okay, now what I will do is that, so if you look as per the diagram, right, so I am taking a control signal as reset. If the reset equal to 0, what should I do? I send 0, right? 0, right? If the reset equal to 1, that means it's not active, I should look at maybe the set value. Again, if the set equal to 0, I should send 1, that's a 1, and of course if both of them are not, let's say, active, I should send current state 0, right? So now later on look at the solution which is given in the slides, and the diagram is exactly matches, but this is a bit more high level. Is that clear? I think we have a glitch, I guess, online, but it's okay, I feel. So the difference is that earlier we were really directing the logic to the D pin and let us say sorry, the preset pin and a clear pin, or the or the PD pin and a CD pin according to the book. The reason is that they are asynchronous and we have a flip flop in the library which does that, but here it is a synchronous flip flop and we do not have a flip flop with a synchronous pins, right. So, now D pin is only the synchronous with respect to the clock. So, that means we have to really redirect all the reset and set logic to the D pin itself. That is what we did. Okay, that is the difference. Yeah, good. Okay. So, now I think these example you should be able to do it. Okay. So, purposefully, so I mean I think this one you should be able to do it. Okay. So, here we wanted to really show the difference between the, again you see, right, in any block. So, there is a kind of a blocking here and a non-blocking here. The actual advice is that not to mix them, but now to tell you something with this example. So, we just mixed it. So, now try to come up with a logic diagram of your own. So, you have to be a bit careful with respect to the right shift value. What right shift we should really have, whether the right shift is a, I mean you try and then you will look at the solution and just try to understand where we might have done a mistake. That is the rule, right, but let us assume that we mixed it, and what will happen, and the way you think and how the diagram comes, you try to come up with your own diagram. Okay. So, maybe you can check whether so touch does not respond. Okay. Okay. So, now so where is the right shift? Okay. Which value of right shift you used? Okay, here the select first is okay, right shift is there. First of all, ask this question: how many flip flops will have? 3, right? Do we have 3? Okay, good. So, one is for the right shift, one is for the check stop, and one is for the select first. Okay, good. So, now right shift logic is nothing but we have to right shift and of course AND gate, of course strobe and right shift. So, we have to update the value. So, that is what we should have. We have, right? Okay, good. Now, for the select first, okay, now you are reading the right shift. So, which right shift you are taking? I mean, what the semantic says, we have to really use, but because this statement is executing after this, right, it is a blocked. So, even though the non-blocking is there, they have to execute after executing the blocking statement. So, now you might have done that, okay, you might be taking the output from the right shift flip flop, but you should not take, but you should really take the latest value of the right shift. So, that is what we are trying to really show here, right. So, right, this is the latest value, right. So, we are not taking from this point to, I mean for the select first, right, we are taking the updated value. This you might have done mistake, that is what I am saying. Is it clear? Okay, good. Yeah. So, maybe again, so try to come up with your own diagram. Now, here, okay. So, here what right shift value we have to use? Either from the flip flop output or the updated value, right. I would say that we should use the updated value, right. So, updated value is already, it is a right shift multiple let us say AND gate with strobe, right, and of those things, right. So, we should really take that one with X flag and calculate the select first. Okay. So, you might have done that, okay, instead of let us say this one you might have taken here, that is wrong, that is what I am saying, right. Yep. So, try to draw the diagram for this one again. So, how many flip flops we have? 2, right? One for, another for, okay. So does FCR output is used by the claim, right? Because you see, right? So FCR output should be really used by the claim, right? In one of the condition, yeah. So I think, right, it will look something like this, but again, if you use a flip flop without a mux or something, it look bit different structurally, but exactly the equation wise it should be correct. Okay, good. Now the blocking counterpart. So earlier, right, so you might be reading the previous value of FCR and all those things, right, but so here it would be different, right. So you need to really use the updated value of FCR. That would be the only the difference. Okay, good. Yeah. So okay, and again if you see, right, so and one more important thing which you can notice here, in earlier case we had both flip flops, right, FCR and claim, but now if you see here, so FCR of course it's on the left hand side, right. What we said, if it is a left hand side variable, we will get a flip flop, right. But now if you see, right, it's computed here, it's used, right, it's a kind of a temporary variable, so we don't really need kind of a flip flop for the, right, the FCR, so we only have the claim. Okay, good, right. So that's all I had, and these are the references, so which use, it's completely from the Bhaskar book, and again as I said, right, so I might have copied the slides from different sources, and I don't own all the slides. Okay, so I mean the last maybe, of course, right, maybe 2.5 hours, what we try to kind of impress on upon you is that, I mean, we'll always have a kind of a thinking that okay, the synthesis tools does something different, we might not be able to understand, right. The takeaway message is that if you can really do with a pen and paper, yeah, I mean the tool is also trying to do the same thing. And again as I said, right, not only you should think in terms of writing the logic, but you should also start thinking in terms of, if I write something, how does the circuit will come like. And as I said, in the hardware what we have, it's a wire, latch and flip flop, and there are clear rules, when does we get a wire, when does we get a latch, and when does we get a flip flop, right. So with that in mind, we can really write a code which is kind of a synthesizable and will not have any simulation and synthesis mismatch, right. And there are some golden rules, right, again. So in modeling the combination logic, use only the blocking, sequential use only non-blocking, and again as I said, right, I mean use only always block for even combination logic, and list all the right hand side variables in the sensitivity list, and then of course, right, using the always blocks have an advantage that you have a advanced constructs like if, else, case and all, we can use it, right. If you use maybe assign, you should only use kind of a long expressions, but that's how it is. Okay, so that's all I have. Yeah, I mean like whatever with that we have learned about the FPGAs, about this Verilog and all, but it's a kind of a semester long course. So but we just try to give a kind of a glimpse of it. So if anybody need, so I think we can also talk in a later as well. Good.